Well, we have a number of different options of what we could do with the nuclear waste, and one of those options is the geological disposal, putting it underground. There are other things have been discussed in the past as to what we might do, but that's the option which is, I guess globally, collectively, we would agree is the best solution.
When you say the word geological, your face lights up. Just going to say that. Hello and welcome to WSP's Positive Impact Podcast. I'm your host, Lucy Siegle. In this series, we explore the ideas, innovations and voices shaping a more sustainable, resilient and future-ready world. Today, we're going beneath the surface, quite literally, to explore how the UK is tackling nuclear waste, one of the greatest technical and societal challenges of our time. We're heading to the intersection of science, engineering and long-term responsibility to understand how WSP and nuclear waste services are using deep geological disposal. Nuclear waste understandably attracts attention, but what is the science actually telling us and where are we now? Well, it's time to dig deep with our expert guests who are disrupting the status quo in their fields. First, we have Professor Chris Jackson, Technical Director of Subsurface Storage at WSP. Welcome to you, Chris.
Morning.
And Professor Neil Hyatt, Chief Scientific Advisor for Nuclear Waste Services and the UK government's top scientific voice on radioactive waste management. Welcome to you too, Neil.
Morning.
We've got a lot to start with, so I'm going to get cracking because we've got a lot to get through. I've got a lot to learn on this subject, let me tell you. Okay, so what I'd love to know first is what is the role of nuclear energy? What role does it play in the UK's energy mix today? And how has that evolved over time? Neil, I'm going to come to you first.
Very good. Nuclear energy generates about 15% of the UK's electricity. And so we have 6 advanced gas cooled reactors. So these are the UK's second generation of reactor design, and a single pressurized water reactor, and that's Sizewell B. So as I said, together they generate 15% of the UK's electricity. And they have come about over 70 years of nuclear fuel cycle activities in the UK, so civil and defence. And we also have a very significant decommissioning industry. So once reactors and nuclear facilities reach the end of their life, they have to be decommissioned and dismantled safely and packaged for disposal, which we'll come on to talk about today. So we have 6 advanced gas cooled reactors which are in the process of defueling, so preparing for decommissioning, 26 Magnox reactors, the first generation design, which are in full decommissioning. So this year marks actually 20 years of the creation of the Nuclear Decommissioning Authority, the body set up to lead nuclear decommissioning in the UK. So it's a long-term project, so over 100 years in duration, and Nuclear Waste Services is one of the operating companies of the Nuclear Decommissioning Authority Group, and so we're leading on the disposal of radioactive waste and its management.
Yes, so we've got a past, a present and a future, Chris. How do you think it's helpful to sort of frame the role that nuclear plays in the UK?
Well, I think when we get on to talking more about the geological disposal of nuclear waste, it's important to remember that we already have nuclear power production in this country, so it's not a new thing. So I think it's understandable when we're talking and we're trying to communicate to the public more generally that something new can seem, intimidating, can be worrisome. But actually, we already have nuclear power production here already. And as Neil just referred to, we have existing waste being generated as a function of us using that nuclear power. So we need to have a conversation about what do we do now to be kind of good stewards looking to the future. So, yeah.
Give us a hint. Where's it going?
Well, we have a number of different options of what we could do with the nuclear waste. And, one of those options that absolutely we're going to talk about today is the geological disposal, putting it underground. There are other things have been discussed in the past as to what we might do, but that's the option which is, I guess globally, collectively, we would agree is the best solution.
When you say the word geological, your face lights up. Just going to say that. Okay, so let's just sort of drill down a little bit. Oh, sorry, all puns intended, obviously. Why is managing radioactive waste such a critical part of the UK's nuclear journey? We've got a hint of that, but Neil, tell us a bit more about why that is.
Right. So at the moment, radioactive waste in the UK is stored at about 20 sites around the country above ground, and that's done safely and securely every day. But that's not a sustainable long-term solution because the radioactive waste has to be repackaged. The packaging has a finite lifetime, and the stores need to be rebuilt. They have a finite lifetime. And as we go through that process, obviously we're spending public money, and we're also exposing our workforce to hazard and risk. And so the Geological Disposal Facility is the exit route, the off-ramp from that sort of uncapped liability and uncapped public expenditure. And so as we'll come to talk about, that involves in placing radioactive waste in a stable, ancient geological formation, 200 to 1,000 meters underground. And there, the radioactivity is isolated from the surface. It's contained for the hundreds of thousands of years that it will take to decay to a safe level so that it can no longer pose a hazard to the environment or to life.
And Chris, this is not unique to the UK, this need, is it?
No, a number of countries around the world have been producing energy or producing power in the same way using nuclear fuels, and they also have waste generated as a product of that. So we're not on our own in having this challenge, and in some ways that's kind of useful to have global peers, if you will, that you can talk to about different solutions and optimizing the process of identifying a suitable site for storing the radioactive waste. So yeah, it is a global challenge.
And so is it a sort of international conversation in that way?
Yeah, absolutely. It's a way of finding out best practice, probably more generally, because the actual solution will differ based on the specifics of the geology in those different areas where that waste is found. So it's not a one-size-fits-all in any way, shape or form. We can have a discussion around some of the commonalities of the challenges we have, some of the scientific and engineering challenges, but then we have to do very much more locally fit for purpose solutions for some of those, from that siting exercise, we call it.
Well, I feel we've trailed this quite effectively. We've got a good build up to this. But what is a geological disposal facility, Neil? And why has it become, in effect, the internationally preferred approach to long-term waste management?
So the Geological Disposal Facility will be constructed, as I've said, 200 to 1,000 metres underground in a stable geological formation. And it will comprise a series of tunnels and vaults into which the radioactive waste will be placed. And those tunnels and vaults will eventually be filled with a clay or cement type material. And eventually the facility will be closed and the radioactive waste will be left in place to decay until the radioactivity reaches a safe level that it can no longer cause harm to people and the environment. So to give you a feel for the project, it's 150 years in duration from sort of start to finish. We'll spend about £300 million a year of public money typically to get to the end point. And we have to take care of not only the radioactive waste that exists today, but also that will be generated in future. So we have to make provision for the waste from future nuclear reactors. So the GDF is also an enabler of nuclear new build and meeting our country's net zero aspirations. So, as Nuclear Waste Services, we're on a mission to make radioactive waste permanently safe sooner. And the GDF is one part of the answer to reaching that mission's goal.
Yeah, it's interesting because there are other solutions that have been proposed over decades to handle nuclear waste, and there is kind of exotic as burying nuclear waste into ice sheets or shooting it into space, or literally putting it into ocean trenches, so putting it down several kilometers beneath the sea level down at the seabed, and all of those might sound like they're an easier solution, but they all come with a whole raft of geopolitical challenges and management challenges that mean that, they sound like good ideas, but they're actually much more hazardous and harder to control and harder to engineer a suitable solution for that. So that's why the GDF has become this international solution of choice, so it's not that it was the first solution that was come upon. Other solutions have been discussed. So
yes,
I think that rigorous decision-making process is important to bear in mind as to where we are now.
And is it that there is one solution that's kind of internationally agreed upon? Or will there be other nations who are looking at some of the other things that you talked about?
I'm not aware that any other nation has seriously engaged in trying to develop an alternative solution. I'm aware that other people are looking at GDF type solutions with local changes based on the local geology and the engineering that's required. But I think it's due diligence to consider all solutions, of course, before selecting the most appropriate one.
Yeah, that's right. So I think the consensus has emerged that the Geological Disposal Facility concept is the best available technology. And as you said earlier, Chris, the implementation of that has to take the natural environment as it's chosen and selected, so the target geology, but it also has to reflect the demands of the waste that we're going to dispose of, so the national inventory. And in the UK, that's a challenge because we've got 70 years as a pioneering nuclear nation. We led on the development of novel reactor concepts. We had an experimental program, a reactor development program, of course, a nuclear deterrent program. And so that's given us one of the most complex radioactive waste challenges in the world. So 773,000 meter cubes of radioactive waste to dispose of in a GDF. But it's a substantial volume of waste. So whilst there's much that we can learn and pull across from international projects, and we work very closely with programs in Switzerland and France, for example, there are challenges and scientific, issues that we have to solve for ourselves because they're unique to our waste inventory.
Well, I mean, you've pointed out how complex it is and the scale that's kind of needed. What type of expertise and collaborations are needed to deliver a project that is this complex?
Gosh, I mean, what a question. So it's,
it's needed.
Almost everything and everyone. So, in a scientific context, of course, it's an incredibly interdisciplinary and rich and interesting field, and one that's been a privilege for me to work in over 20 years. So, it's material science meets chemistry, meets physics, meets earth science. It all has to be engineered and delivered. And, whilst we do have, specialists who are experts in those subjects, we also have to do the integration. And so, as I've gone through my career, that's been something I've been increasingly more interested in, and having to work across a sort of wide range of disciplines. But then, of course, this project has to be brought into reality. So we need to deliver it in the UK with the consent of our communities. Inevitably, it has a political dimension. So we need political support and treasury support. We have to deliver the project to deliver value for taxpayers, because this is ultimately public money, so it's all got to be delivered as a program which is effective and efficient, and it's a first of a kind in that respect. So we need all skill sets. There's a place for everyone in the GDF project, I like to think.
And in terms of the engineering, we need contractors, we need people who dig holes in the ground safely and securely, who can actually execute the vision of the scientists and engineers and the designers. And then Neil kind of hinted at it as well, but the general public, I mean, it's as much a project for us as a nation, including us as a broad public, as it is for a specific set of scientists and engineers. Because we, as we, may talk about later, this fact that it's a consent-based process, that we need the public to kind of collectively, or one certain, communities to permit us to construct the GDF in that locale, then it is truly a project for everybody.
I do want to come back to that because it's a very, very interesting area. But I wonder, could you talk about the geoscientific kind of input and how you collaborate on that?
Yeah, so Neil's mentioned a few important parameters already. The GDF is going to be built between 200 metres and 1,000 metres below ground. He's used the word stable twice, a stable geological rock formation. And by that, kind of what he's hinting at is we need a large volume of rock which is relatively stable. By that we mean that it's limited in terms of like faults or fractures within it. It's not in an area where there could be large earthquakes and things, because we need this engineered facility to be safe and withstand those natural processes. So what we need to be able to do is collect rock samples and image the rock mass to make sure it's of the suitable size and composition. So one thing we wish for in the GDF is that the rocks are what we call impermeable. So we want those rocks to not have a lot of space in them to allow fluids or gases to flow, because as Neil has alluded to, we want to keep the radioactive waste and anything that might come from that waste partitioned away from the near surface where we live and where we have what we refer to broadly as the biosphere, where life on Earth exists. So that's what we need to do with the geology, is really kind of pick away at the physical properties of those rocks to make sure that they're suitable for storing rocks in for long. I'm going to use the term long term because we've not really talked about how long we need to keep it there, but we need to keep it there for a long time.
Well, let's talk about it.
Yeah.
Well, what do you mean by long term?
So we make our safety case over a period of a few hundred thousands of years. That's the time that the radioactivity takes to decay to a level where it can no longer pose a hazard to the environment and to life. And so the way that we do that, of course, as Chris has said, in the very long term, it's the rocks that do the hard work for us because, water moves through them very slowly, gas moves through them very slowly. And because it takes a long time for radioactivity to move, that's over that period of time, it's decaying all the time, of course. So the rocks are very important. And then we have two other parts that really sort of form the strength of our safety case. One is that the waste itself is unreactive, and is passively safe. And then the second is the engineering interface between the waste and the natural environment, what we call the engineered barrier systems. So these are, for example, what we fill the caverns with, the clay and the cement material, the plugs and seals to the facility. And all this working together, what we call the multi-barrier concept, is what delivers isolation from the surface and containment of the radioactivity until it's decayed to a safe level.
How would it look?
Oh gosh, so it's if you imagine kind of a tunnel down to the surface, a gradually sloping drift, and then there'll be a receipt area where the waste packages kind of come in as they've descended from the surface facility, and then they're dispatched either to vaults, so typically where we would dispose of the intermediate level waste in boxes or drums, and so these will be sort of underground caverns. They'll have a look and feel of some of the surface facilities that we have today. So, there'll be cranes to move waste into place and set it into place and so on. And then we'll have a series of what we call disposal tunnels. And this will be for the high-level waste glass, spent nuclear fuel, nuclear materials. And these have the property of being heat generating when they're in place. And so we have to space them out in order to manage that heat output and its dissipation. And so, that's a great example of where sort of engineering and the inventory comes up against the host rock, because the rate at which the host rock dissipates heat is something that
really
we need to know.
Yeah.
And that's where we look to contractors like WSP to help us get an investigation of those physical properties.
Yeah, we want to know about the thermal conductivity properties of the rock. So how wicking, do those rocks wick away the heat and cool the waste down?
Exactly.
Or do they insulate it like a warm duvet and actually cause maybe more demands on the engineered barrier part of the solution, because suddenly it's getting very hot in there? Because remember, it's not over a week or a year. We're talking about tens of thousands of years or hundreds of thousands of years. So those processes are going to go on for a long time, so they can generate a lot of heat.
And can that heat be used?
There are discussions about using some of that heat. So there are some preliminary studies looking at geothermal recovery of the heat. So I've heard about projects where people have discussed lining the kind of the facility, if you will, with what we call a borehole heat exchanger. So basically passing down cold fluid, producing hot fluid because you're drawing the heat away. That comes with a whole load of lots and lots of challenges to do with building the safety case for the nuclear, the GDF itself. But there are those things being talked about. And I find those things encouraging, because when you talk about future ready, as you did in your introduction, we should be thinking in a really innovative way and really challenging ourselves to think about how do we make facilities sustainable, because that geothermal energy could be used to power the lights or the cranes or some other aspect of the GDF, and therefore reduce our overall carbon footprint.
Yeah, I think that's right. I think, we have to build the GDF with the technology that we have today, and there's certainly room in the future for innovation. Its fundamental principle, though, is one of passive safety in the long term, so that we rely on the natural evolution of the system to ensure its safety. And we've painted quite an exciting picture, I think, of the GDF and its conceptual nature and what it does. But ultimately, it's not going to be a very exciting place. It's going to be a place where corrosion happens very slowly, and time in that sense passes very slowly.
It's not going to be like the library scene at the end of Indiana Jones, where he goes in to place the kind of artifact at the end. Some grand facility. But that's the point. Is it's a working environment. It's not a museum.
Yeah.
It's an actual place to safely secure nuclear waste for hundreds of thousands of years. So it's kind of, dare I say it, the science and engineering is incredibly exciting. It's incredibly challenging, but the product is going to be something which is going to do its job, and that's the most important thing.
We want the product to be as boring as possible in many respects.
Right.
Yeah, and Neil kind of described what it's going to look like. I mean, I found it very powerful to go into some mines in Cheshire. It's a kind of slightly aspects of the geology is comparable to some places we might consider, but other bits are different. But like when you go in a mine, it is like a big hole in the ground. There's lots of like rock exposed on the walls. They don't have an engineered facility as well. But I think that's a very good mental starting point for people to a good lift-off point for people to imagine what it would be like down there.
Absolutely.
Yeah.
And when we're working with our stakeholders, be they local or national government or our communities, we have very good links with our counterpart programs in France and elsewhere, and in Finland, where we can take them to, facilities which are, in the case of Finland, an actual GDF that's ready to go and will dispose of its first spent fuel by the end of this decade. Or in France, an underground research lab, which is essentially, a demonstration, of what a GDF will be like, and has developed all the technologies needed to develop a GDF in that location. And being in those environments, it really brings it to life. Otherwise, it's all a bit theoretical and conceptual.
Yeah, it's absolutely one of the geological challenges is how do you take yourself as a trained geologist or as a scientist more generally, and the public then as well, how do you take them into that environment and make them understand what it's going to look like, what do we know about the rocks when we're using these words like stable and impermeable, and trying to give people a bit more of a hands-on experience and exposure to that is a really powerful way of communicating some of the complexities, but also to elevate ourselves in terms of, this is how we know this, and this is how we measure this thing, and this is how we build a safety case. It's not just guesswork. It is based on, a number of observations. It's based on some quantitative science and engineering solutions, and that's taking people places is really useful.
It is, isn't it? And I've heard you speak very powerfully in the past. I mean, you're the master of communicating this stuff. Well, you are, because it's very hard to communicate what goes on beneath your feet, isn't it?
It's hard. I mean, it's hard for me in some ways with 25 plus years of experience doing it, and that's the challenge is when you're communicating to people, is really thinking through it yourself and taking yourself back to being a teenager when you were asking those same questions, and not to presuppose that people will have the same level of professional training that you have.
Yeah, and it's very surprising when you're talking to members of the public and you ask them what they think the underground is like, and all sorts of ideas come up, like underground lakes, or it's just black, or it's all kind of like magma, and and you're right, you have to kind of put yourself in their position of not necessarily having a high degree of knowledge and try and sort of think your way and feel your way to the understanding you need to develop from their knowledge state and their point of view.
But as you say, I mean, you can go and see a mine in Cheshire or Derbyshire, which will give you I suppose people have been very influenced by the Lord of the Rings franchise.
So I was about to say exactly that. One of the biggest challenges I find when talking to people is not necessarily that they have a neutral understanding what the Earth's subsurface looks like. It's that they actually have an informed understanding based on movies.
Right.
I would say that is honestly the number one thing I've come across, because Journey to the Centre of the Earth, any sort of like film featuring The Rock where he goes into the earth to stop an earthquake, they all have these incredibly visceral images, which are quite frankly way more exciting than what the actual subsurface of the Earth looks like, but also more seriously, much more dynamic and much more dangerous. And actually, going back to that word stable, there are large volumes of the Earth's surface where the geology is stable, and there's no earthquakes, and there's or limited seismicity, I should say. And actually, that's what we would strive to look for a GDF facility. It's not like the Hollywood version of the Earth's subsurface. So it is a big challenge, because it's It's
Yes.
a widely held view.
Yes, and you're sort of trying to get people interested, but also trying to tell them it's boring and stable and it's fine. So it's a complicated mission, isn't it? So there are some really complex technical and societal challenges that we're talking about here. Neil, would you just, tell us about a couple of those challenges and how you're going about solving them within this project?
Yeah, okay. I'll sort of start perhaps at a high level and talk about one of our near-term goals, which is to provide a recommendation to government on the first sites to take forward for deep borehole investigation of the subsurface. And that will happen this financial year. And so, as you can imagine, that is incredibly complex as an integration. We need the technical evidence, our understanding as it is now of the subsurface geology and how we might develop a geological disposal concept, the engineering to deliver a GDF safely, the community willingness, and then aspects to do with, for example, value for money, what it would cost to deliver a GDF in that location. And so, we have incredibly detailed studies that need to sort of essentially be boiled down. They need to be synthesized, and we need to elevate, the key messages and the risks that matter. And so that's a piece of work that we're doing right now and that I'm involved in. And I think, where I can really help that is being, a lot of my job is about really understanding, what are the technical risks we're carrying? What are the really important risks, and being able to elevate those and have them understood in the right way that decision makers can be effective. And so this is a really important milestone for the UK programme, because it will be the first deep investigative boreholes that we'll do since the NIREX programme that finished in the 1990s. And our sort of first step towards getting a real understanding of the geology at the locations we're interested in.
Yeah, absolutely. So we in WSP and myself is involved in that team where we've been doing some of the original site characterization work. So we've been looking at some legacy, we call it, so older borehole data and some older images of the Earth's subsurface to try and at least start to see if some of these sites have, broadly appropriate geology to host a GDF, and sort of getting more and more information about what the physical properties are of the rocks in the subsurface. Specifically, as Neil says, that then we can target, I would call them more bespoke boreholes. So these are boreholes that are drilled specifically to collect data to characterize a rock mass for the storage of a GDF. Some of the old borehole data was drilled for oil and gas or for water.
Right.
They contain very useful information, but not of the targeted nature of which we'd wish to build the safety case or the engineering design case for the GDF. So it's a really exciting time for us. I mean, a number of staff in WSP and other companies in the supply chain, we've all been working very hard at trying to understand as much as we can with what we have, being mindful of the fact we're not going to know everything, and that we are going to have to propose locations for additional borehole data to increase our knowledge. And let's be true, when that data comes in, it may be very strongly supportive of the initial sense or the initial appraisal of those sites. It might be positive and say, okay, it's all good to go, but equally it might challenge us. I mean, that's just the reality of geology.
Wow, yes, of course. And there's been a sort of hiatus then. So if this investigation hasn't really been done at this level since the 1990s, I think you said, have there been changes? Has the science progressed? Has the technology progressed? Do you do things in a slightly different way?
I think we have some drilling approaches that have kind of improved about, we'll be able to collect better data and be able to collect data maybe more cheaply, and therefore be able to collect more of it in different locations so you can more fully characterize the rock mass itself. There's definitely advances there. There's definitely advances in research as well.
Absolutely, yeah.
I mean, research has moved on a huge way in our understanding of rock fluid gas reactions and the reaction between fluids and gases and engineered materials as well. So we need to re-up all of that advanced knowledge into this new program rather than sort of starting off in the mid-90s is not really useful.
Yes.
So the last 30 years has really been about putting in place the evidence base to demonstrate that we can deliver a GDF safely in a generic context. So what I mean by that is, developing an understanding of the way, for example, the waste packages will behave. We call them generic disposal environments. So how it would evolve, for example, in a salt deposit is different from in a claystone. And so we have gathered international understanding. So we've got on top of the best of the international knowledge, and we've also developed our own knowledge. So before I joined NWS, I was a contractor for NWS's predecessor. And so I did a lot of the work on understanding how high-level waste classes will evolve in a disposal environment, which contain the radioactive waste from nuclear fuel reprocessing. And so we have a good understanding of the basic mechanisms of how glasses corrode. And what we're doing now is trying to further that understanding in the sort of specific groundwaters that we might encounter at depth. And then as we progress with site characterization and deep borehole investigation, we'll have real groundwater samples. So if you like, our knowledge increases as we go forward, and we learn more about the environments we'll be disposing in, and the uncertainty in our knowledge decreases as the knowledge increases. So that's the sort of journey we've been on over the last 30 years.
This has been a very exciting conversation, but this podcast is about positive impact. So the last thing that you get to do is to choose something. If you had the power right now to make a positive impact in this space, what would you choose to do? Chris, let's start with you.
I feel I'm already doing that. I'm working on one of the most exciting and challenging kind of subsurface focused problems that the UK's ever seen and may see for a long time still. And it's a real pleasure to be doing that. I feel that it is making a positive impact. As Neil says, it does two things. It helps us deal with legacy nuclear waste. So this is waste we have already. So if we wish to be seen as good ancestors by future generations, then dealing with it is really something to feel really proud about. And also, because these facilities may receive nuclear waste in the future from new nuclear power stations, which are being built to help us achieve our net zero ambitions, then that's another reason to be really kind of feeling positive about being involved in this programme, not just for me, but for WSP more broadly.
Neil?
Yeah, I think, for me, it would be, if I could really change something, it would be for the public to have a really good understanding of the risk posed by radioactivity. And I think part of the challenge we face is that there's a low degree of knowledge. The industry has not always conducted itself in a transparent way. And, where things have gone wrong, Chernobyl, Fukushima, and so on, there have been very considerable and significant impacts. And so, the public in some ways are rightly, they're right to be concerned, and they're right to want to have answers. And it's our job to provide them with answers that they can understand. But I think, where we sometimes find ourselves not necessarily in disagreement, but it's hard to find common ground, is because that perception of risk is not well founded, and that's part. That is on us. We need to be able to, I guess, upskill the knowledge, and part of the way we need to do that is to provide people with experiential opportunities to learn. Yeah. So I guess that's something that I'm keen to work on as I come towards the closing chapters of my career.
Come on!
Well, and I suppose I've been thinking a little bit about this podcast, how I would answer this question, and I've been hugely privileged to work in this area for over 20 years, and my mind is turning to what comes next and how we maintain that. What I bring to this project, which is the independent scrutiny of somebody who's studied the subject from many different perspectives and across many different disciplines, and that we ensure that we maintain the scientific rigor and quality of our evidence base, over the 150 years that it's going to take to get to an endpoint.
We've dealt with a lot of time horizons, a million years now, personal time horizons, and mine is that we're out of time. So thank you for such an incredible, engaging, mind-blowing conversation. I really, really enjoyed that. And that's it for this episode of Positive Impact. So a huge thank you to Professors Chris Jackson and Neil Hyatt for sharing those deep insights into a subject that, let's face it, is often misunderstood, but absolutely vital to a sustainable future. I have to say, I think you've made a very compelling case. Now, if you found this episode enlightening, don't forget to subscribe, rate, and share the podcast. You can also find more about today's topic, including extra resources and links in the episode description. So thanks for joining us, and we'll see you next time as we continue exploring the ideas shaping a smarter, greener world. I'm Lucy Siegle, and this is Positive Impact. Goodbye.